Hello, and today we're going to have a look at some linear relations, which is effectively just what we've already looked at, but we're just going to go into a bit more detail. So here we go. Here is a starter question. Have a go if you want. As always, starters all to do with what we did last lesson, just making sure you can remember it all. I find it's always useful to do it, just to recap everything, just so when we go into it, it's like, oh yeah, I remember what we talked about and what we can do. So have a go. We'll go through it very shortly. Okie dokie. So the graph on the right shows Pietro's distance from school D during lunch. So it says it right there, right? It says the distance is D. So it's on the left hand side, and then on the bottom it obviously has time. We talked about how that's going to be independent and dependent. Let's do it. So during what time intervals was Pietro moving away from school? So it says distance from school, so therefore any time the distance is going up, that's the time he's moving away from school, right? So we would say the time from 0 to 20, he's moving away from school, and 25 to, is that 40? 40, right? And just in case you're not with me on that, he's moving away from school here, then he stops for a bit, and then he moves away from school again, and he stops for a bit, and then he heads all the way back to school. And we know that because D is distance from school, and so when he comes back to 0, he's 0 distance away, if you will. During what time interval was Pietro moving towards school? As I just said, that's this part right here, so it's 55 to 65, and that's what you would say. When the pen works. Yep, there we go. 55 to 65. What is the furthest distance that Pietro was from school during lunch? That is literally the highest part the graph goes to. For some reason, whenever I teach this, some people think the answer is 2 because the graph goes all the way up there. But no, this is Pietro here. So where does he go up to? He goes up to 1.5, doesn't he? So that's the furthest part away. So that's 1.5 kilometers. Okay, kilometers, it says it on the left. The school's lunch period occurs from 11:30 to 12:30. If Pietro left school immediately at the beginning of lunch, how late was he when he arrived? Well, you know from 11:30 to 12:30, that's 60 minutes. So he's obviously he's 5 minutes late, isn't he? Because it says here, he should have been 60 minutes, he's 65 minutes, so therefore he's 5 minutes. During what time interval was Pietro not moving? So this is the reason this question is a bit misleading is because it only says distance and it doesn't say anything about moving or not. So he could actually be the exact same distance away here and moving. Like imagine you're here. If I move around in a circle, I'm the same distance the whole time. And I'm still moving. So it's a bit of a silly question, it should be worded better, but we're going to assume in these parts right here is when he's not moving. We're just going to say that he stopped instead of moving around in a circle or whatever. So during what time interval? That's going to be 20 to 25. And also, what's that, 40 to 55? 40 to 55. During what time interval was Pietro moving the slowest but not stopped? So this one, what you're doing is you're looking for the slowest, like the least amount of slope, like the slope that doesn't like have the highest gradient, if you will. So basically the line that's the flattest to the floor. So this is, I hope you agree, the flattest one, right? Because you can see that all the others are a bit sharper. But even if you weren't okay with that, you're like, I'm not entirely sure. If you look at just the numbers, in this one, in 20 minutes, he does 0.5, right? In this one, in 15 minutes, he does 1. And here, in 10 minutes, he does 1.5. So even if you weren't 100% sure, you can, just because of the size of the slope, you should be able to tell just by the numbers as well. So during what time interval was Pietro moving the slowest? It was between 0 and 20. What time was he moving the fastest? Again, we've just worked that out. It's the one he's coming back because he realizes he's late, I guess. So that's 55 to 65. Determine Pietro's speed in kilometers per minute during the first 20 minutes. So because he's driving, because he's going 0.5 kilometers in 20 minutes, and it's asked per minute, right? Then what you're going to do is you're going to divide this by 20, aren't you? Because you want this to become 1. So you divide that by 20, and so you divide this by 20, and I'm going to call it 500 meters. So that's going to be divided by 20 is what, 25? So 0.025 kilometers per minute. Determine Pietro's speed in kilometers per hour from 25 to 40. So from 25 to 40, he does 1 kilometer in, 15 minutes? In 15 minutes? And it said it wants it in hours. So what we're going to do is we're going to times it by 4, aren't we? Because 15 goes into an hour 4 times. So if we times this whole thing by 4, that would get us to an hour. So therefore he does 4 kilometers in 1 hour. So I'm running out of room here, 4 kilometers per hour. And then the last question, it's quite a complicated question, and it's one of those where I don't think it's worth going through today. But basically, it says, what is his speed in his journey back to school? And so what you can see here, if I just very quickly go through it, I'm not going to go into massive detail. You can see he does 1.5 kilometers per minute. And so you have to turn minutes into seconds by dividing by 60, right? And I know normally you think, I'm times them by 60, but because it's per minute, you're actually dividing by minutes. So you're actually going to divide by 60 to get to seconds. And then you need to turn the kilometers into meters. So you're going to then times that by 1,000. And without actually putting the numbers in, you can already see it's quite complicated. But if you understood what I've said there, you've understood. But I'm going to tell you right now, I'm not going to have a question like that on the test or assessment. So don't worry if you don't. We will be doing stuff like that later. But it's just there to show you how far we will go. But in general, I really don't mind if you don't understand that right now. Okay. So, linear relation. The word linear relation genuinely is just a fancy word for a straight line. That's all it is. It's like, hey, well, that's a linear relation. It's just a fancy word for a straight line in relation to two things. So, if, for example, I think about money, if I earned $15 an hour, right, every single hour I'd earn $15. That means in 2 hours I'd have $30. In 3 hours I've had $45. And you can see that as one goes up in ones, so time goes up in 1 hours, the money goes up in 15. It's a linear relation. It's a straight line, isn't it? So as long as we keep going up in 1 hour, we keep going up in $15. This, weirdly enough, is a linear relation. The official language, this is the official language that we should be using, is the dependent variable changes at a constant rate as the independent variable changes by a constant rate. And that's what I've kind of said at the beginning, wasn't it? It goes 1, 2, 3, it goes 15, 30, 45. They're both going up at the same rate for each number. Okay, so you can tell something's linear, you can tell if it's a linear relation if it's a straight line. So, example then, which of these are a linear relation? We can see it right here. This is linear, this is non-linear. This is non-linear, this is linear. Doesn't matter if it's going up or down. Is it a straight line? That's basically it. What does it mean for a relationship between two variables to be a linear relation? It means as one variable goes up in a constant rate, so does the other. You could be even more specific by saying the exact phrase I said earlier, this phrase over here, this phrase on the bottom. But honestly, as long as you say something that shows me you understand one go up, other go up at a nice rate, you're good. Okay, so your quick go, have a very quick go, see if you can do it. That literally is level 2, level 3, level 4 from left to right. Have a quick go, tell me what you think. Okay, so determine if this graph represents a linear or nonlinear relationship. This is a linear graph, it's a straight line. Determine if this graph represents a linear or nonlinear relationship. It's a nonlinear. Why? Because it's not a line. I'm not going to explain it, but that is it. It's not a line. Ty earns an hourly wage of $15 per hour. Would the relationship between his hours worked and money earned be a linear or nonlinear relation? It would be a linear relation because for every 1 hour, he gets $15. It's a linear relation. And you would say the same thing as earlier, as one goes up, the other goes up. Determine if this graph represents a linear or nonlinear. It is nonlinear. Nonlinear. And I think this came up in the last video, and I talked about how it's called a sinusoidal wave. That comes up either in it's 3U or 4U. So when you're ready for that happens. Determine if this graph represents a linear or nonlinear. It's linear. A rabbit farmer starts with 10 rabbits. Each generation of new rabbits has twice as many. So we have 10 rabbits. So like in 0 weeks, we have 10 rabbits. And then each generation, it doubles. So it becomes 20. In the second generation, it becomes 40. In the third generation, it becomes 80. And very quickly, you can see that is not linear because that's doubling, isn't it? Non-linear. And you would say, I don't know, there's many ways to say this. You could either say it wouldn't be a straight line, or the on the right, it's not going up by a constant amount. Whatever you want to say there, who cares? Okay. Linear relations from a table then. So, sorry, give me a second. There we go. So if we get a table of values, how would we know if it's a straight line? And so that's basically what we just had in that last question, wasn't it? And the key to this is all about first differences. We could plot the points, but obviously that takes time. But instead what we can do is do something called first differences. And it seems incredibly complicated originally, because the number, like, first differences, what do you mean? But genuinely, all you do is find the differences for everything that's happening. So I'll show you an example. So as I said here, find the differences between both columns. If you divide each difference on the right by the difference on the left and it's always the same, then it's linear. If it's different, then it's not linear. And this is important because sometimes some of the questions won't be, like, it won't go 1, 2, 3 on the left. It might go 1, 2, 4, 9 on the left, because that's how things work. But the differences between here don't have to be the same as long as the numbers on the right, like whatever's happening here, divides by this number over here, and it's always the same. And if that made sense, wonderful. And if it didn't, don't worry, we're going to go through some examples. But just don't automatically assume that something isn't linear just because on the left it skips a few. It's okay to do that. It's just more importantly if the differences when they divide each other are always the same. Let's have a look. So, on the left, what's it going up by? It's going up by ones, right? 0 to 1 is 1, 1 to 2 is 1, 2 to 3 is 1. If in doubt, subtract them. What's going on the right? 18 to 20 is 1, 20 to 22 is 1, 22 to 24 is 2. Is 2. What am I saying? It's 2. And then 1 and 2. And you'll see here, if I do 2 divided by 1, i.e. This 1 divided by this one, if I do this 1 divided by this one, I get the same as if I do this 1 divided by this one. And I get the same as if I do this 1 divided by this one. And because of that, it's always linear. Cool? So is it linear relation? Yes. What about this one? What's happening here? It's going up in ones, right? 1, 1, 1, 1. What's happening here? It's going down in 3, down in 3, down in 3. And this was supposed to be minus 4. Please ignore that. That's me being an error. And it goes down minus 3. So then, what happens? It goes, well, negative 3 divided by 1 is the same as negative 3 divided by 1, etc., etc., so it's linear. Here's a perfect example of where it looks like it's not linear. Because you're like, hold on, this is going up in 1, this is going up in 2, then it goes up in 1, then it goes up in 2. That doesn't look linear, but if you look here, it goes up in 3, then it goes up in 6, then it goes up in 3, then it goes in 6. And as we said a second ago, it's not about the jumps that's happening, it's about this divided by this. 3 divided by 1 is 3. 6 divided by 2 is 3. 3 divided by 1 is 3. 6 divided by 2 is 3. So it's still linear, even if it doesn't look it in the table. It's all about the representations of, like, the first differences. Okay, so your go. What are the first differences? Go. Are they linear, are they non-linear? Okay, hopefully that's enough time. Let's go through the questions. If it allows me to change back to red, that'd be lovely. Thank you. Okay, so what happens here? This is going up in ones, right? This is going up in 4s. This is going up in 6. Oh, what am I saying? 4, 4. It goes up in 6, it goes up in 6, it goes up in 6, it goes up in 6. So 6 divided by 1 is all that's happening, so it's linear. Again, these are going up in ones, which is wonderful. These are going up in 1,000, then it goes in 1,500, then it goes in, what's that, 2,250. It's pretty obvious this is non-linear, isn't it? Yeah? What about here? It's going up in 5s for each one, 5, 5, 5. What's going on here? Negative 3, negative 3, negative 3, negative 3. All of them are negative 3 divided by 5, so that is linear. What about here? It's going up in 1s. It's going up in 125s, I believe. It's going up in 125. Going up in... Oh, it's not. That one's 75 cents, isn't it? I'm having a bad day for maths. Would you be able to do this for a living? I'd like an eraser, please. Thank you. So that's 75 cents, isn't it? Oh, no, come back. That's 75 cents. Yeah, that's what we like. Yep. Thank you. Yep. So that's 75 cents. 75, 0.75, 0.75, 0.75. So it's linear again because it's 0.75 divided by 1. What about here? These are all going up by the same amount, so it's all 2s. This is going down by 2, then up by 6, then up by 14. It's pretty obvious. I don't even have to divide this. It's pretty obvious. It's non-linear, right? Non-linear. Here I'm going up in 5s, 5, 10, 15, 20. They're all going up in 5s. Here it's going down in what? Is it 3.4s? So negative 3.4, negative 3.4, negative 3.4. It looks like they're all doing the same. So they're all negative 3.4 divided by 5. And so it's linear. Okay, apart from me making silly mathematical errors today, I hope that makes complete sense. And that is how we know if something's linear or non-linear. Okay, let's go over what initial value is. Now, we are not very good with words. I've said this a million times. Mathematicians, it is exactly what it says. Initial, if I ask, hey, what are your initials? You'd be like, oh, it's like my initials are JB, right? That's the first letter of your name. Well, first letter of each part of your name. It's the same thing here. It's the first value. But what's most important is the first value of when x is 0. So let's have a look what I mean by that. Yeah, that's what I want. Yeah. As you can see, big fan of this new thing. Yeah, lovely. Okay, can we maximize? No, we can't. Oh, yeah, good. Can we do that? Oh, good. Yeah, yeah. We're having a wonderful time. Yeah. Honestly, what is happening? There we go, I guess. Okay, well, good for it. Okay, so mathematicians aren't the best of words. If it sounds like it probably is. The initial value is where the graph starts. In general, we say that's when x is 0, right? If we think about axes, we can see axes. When x is 0 is when the graph starts. So whatever the value is at your line, that would be the initial value, right? It's the same for tables. We just want to know what the value is when x is 0. That is when does the graph start? It doesn't matter if the graph starts before it as well. It doesn't matter. I want to know when the graph starts on our axes, when x is 0, right? So if you don't have when x is 0, you go back until you do, right? If it's a table and you can find first differences, you know what's happening. You know if it's going back or not. In a graph, if, for example, we have a horrible graph and it looks like that, yeah, what you would do is you would like trace it back to find the initial value. In a table, right, if it doesn't go all the way back, use first differences to go back to see what the number would be. All right? Cool. So here's an example. What is my initial value, right? As I said, the initial value is when x is 0. So the second you see x is 0, you can see the initial value. So this initial value, I'm just going to put it IV, hopefully you're okay with that, is 3. This initial value is 18. This initial value is -6, because as I said, it's when x is 0. It's not when the graph actually like starts, which I guess you could say is -1. It's when x is 0. What about this one? Oh no, there is no x equals 0. There's no oh no. But you can see here that this is always going up in 10s. And you can see here it's going up in 3s. So if it's going up in 3 each time and it's going up in 10 each time, if I want to go back to 0, I just go back by 3, don't I? And I get 9. So my initial value here is 9. So it's a perfect example. If you're not given when x is 0, you can always just work it out by going backwards or forwards. And as I said with the graph as well, if I was given a graph like this, let's just go like this. It's quite easy to see, hopefully. If I was given a graph like that and said, what's the initial value? You would just trace it back until you realize what it is. Okay, so I better go. You have a go. Tell me what the initial value is. Off you go. Okay, let's go for it. So some of these are just really, really easy, right? Initial value of this one, 2. Initial value of this one, 2,000. Initial value of this one, 20, right? X is 0, so therefore it's very easy. For these ones, you have to find out what's happening. So luckily this is going up in 1s, which is lovely. This one's going up in 75 cents. Notice how I didn't get it wrong this time. Second time's a charm. So then, if I want to go back to 0, I need to go back 75 cents, and I believe that's 7.75. So if you've got 7.75, then well done. What about here? Easy. What about here? Well, it's going up in 5s, isn't it? And this one's going down in 3.4s, I believe. So if I want to go back to 0, I have to go back to 5, which would be add another 3.4, and then go back another to go to 0, wouldn't I? So effectively, I'm going to go back twice. So I'm going to add 3.4 twice. So I'm going to add 6.8. And 6.8 plus 4.6 is going to be what? 11.4. So 11.4 is my initial value. What about these? It doesn't matter if it's linear or non-linear. What I will say is non-linear tables are very hard, right? Because obviously you have to figure out a lot of things. And in general, I won't really ask you that. But in a graph, I will, because you can just follow the graph. What's the initial value? 9. What's the initial value? 16. What's the initial value? It's between, let me just zoom in to make sure everyone's comfortable. It's between 20 and 24, and I'm pretty sure that's right in the middle. So if you're comfortable with saying that, that is 22, isn't it? Right, 22 is right in the middle of 20 and 24. Okay, so we have learned first differences. Oh no, what are you doing? Let's try again. So we've learned that. We've learned initial differences. So we learned first differences. And we learn initial value, which is wonderful. So now we're going to talk about rate. And I'm going to be brutally honest, rate is a word which comes up so often, and you've already figured out what it is. You've already used it. It is just literally what is happening with the first differences when you divide them. You know, when you divide the first differences, that is the rate, because effectively it's what's happening when one thing happens. So rate is how much the dependent variable goes up, down, if the independent variable only goes up by 1. Sometimes it's easy. If the table goes up by 1, then just whatever the right-hand side goes up by is really easy. However, if your x goes up by more than 1, well then divide the y by the x. In other words, just divide the right-hand side of the table by the left-hand side, right? It's difference in the y over difference in x, or some teachers call it rise over run. I don't mind which one you use, or up divided by right. I don't care which one you use as long as you get the right answer. But what I will say is as you get higher up, this one tends to come up a lot more, especially in grade 11. So if you want to start using the right language, that might be good, but that doesn't really matter for now. Okay, so how do we find the rise or run? Let's do it, or the rate. So literally, as I said, all you need to know is how much it goes up per 1. So this one's quite complicated because like as we go across 1, how much they go up. Now you might recognize that goes up by 0.5. But if you're not sure, what you do is you just pick 2 nice points. And I say they're nice points because I can actually count them, right? Like if I just like be over the top here. Yeah, there we go, thank you. If I just be over the top here for a second, and now I've got to change pen, yeah, there we go. It's not going to work, is it? The reason I picked these 2 points is random for one, but most importantly, I can read them, right? I know that this one says 2, and I know this one says 4, and I know this one says 6, and I know this one says 6. So what I need to do is I need to know how much it goes up, and I need to divide it by how much it goes across. So how much does it go up? Well, it goes from 4 to 6, so it goes up by 2. How much does it go across? Well, it goes from 2 to 6, so it goes across by 4. So then my rise over run, or my change in y over change in x, or whatever, my actual slope is just 2 divided by 4, which is 0.5. And we kind of guessed that over here, didn't we? We're like, pretty sure that's 0.5. But my point is, any line, you can just do exactly what I've done there. You pick 2 lovely points that you can read everything, and then you work out how much it went up by and how much it went across by. If you're not 100% confident what I mean when I say lovely points, for example, I wouldn't pick this point. Why wouldn't I pick that point? Because even though I could probably guess that's 4.5, I've got no idea what that is. 5.1, 5.2, 5.3, no idea. And that's not a nice point. So we pick nice points that we can read. Okay. What about these other ones? Well, tables are unbelievably easy. Just tell me the first differences and then divide them. So this is 1, right? That's 1. This is 2. So then just do 2 divided by 1, which is 2. There's your rate. What about this one? This is going up in 1s. No, it's not. Hold on. It's going up in 1s. And then this goes up by 2. And then this goes up by 1. And I think that's a typo. I don't think I meant that. Hold on. Because everything's linear in it. Let's just keep that as 2. Let's keep that as 3. Just to make life easier. I don't want to... It's supposed to be linear for now. So it all goes up in 1s. This goes up in 2s, isn't it? It's increasing by 2. So then again, my rate is 2 divided by 1, which is 2. What about this one? Oh no, the numbers are horrible, are they? This goes up in 10. This goes up in 3. So it's always y divided by x. So it's 3 divided by 10, which is 0.3. You can keep it as a fraction, and the reason you're allowed to do that is because we're in maths, and this is where fractions are. Anyway, hopefully that makes sense for rate. You have a go. Okay, here we go. So, rate for this one goes up in 1, goes up in 1, goes up in 1. This one goes up in 6, goes up in 6, goes up in 6. So the rate is 6 divided by 1, which is 6. This one goes up in 1, goes up in 1, goes up in 1. This goes up in 1,000, goes up in 1,500. This one doesn't have a linear rate, so we don't have to do it. Don't have to do it. It's not in the grade 9 curriculum yet. Okay, what about this one? This goes up in 5s. This goes down in -3s. So what's the rate? It's -3 divided by 5, which is -0.6. What about this one? Goes up in 1s, goes up in 0.75s. So do 0.75 divided by 1, the rate is 0.75. What about this one? Goes up in 2s, goes up in 2, so down in 2, and then goes up in 6. Not linear, don't have to do it. What about this one? Goes up in 5s, goes down in 3.6. So then it's -3.6 divided by 5, which is -0.18, is it? 0.72. Cool. What about these ones? Can we find the rate for these? Well, the linear one we can. So, what's happening in the linear one? What's happening in the linear one? It goes from 9 to, is there any other nice points? None of the points are nice, are they? I guess this is a fine point. So then we find the slope. It goes down from 9 to 0, that's -9. It goes across from 0 to 7, so that's 7. So then we do change in y, we change in x, -9 over 7. Can you find the rate for things that are non-linear? I don't know what -9 over 7 is, but as I said, you can keep it in fractions. Can you find the rate for these? You can, but not in grade 9. You start doing finding rate of stuff, and I want to say grade 12, especially when it's non-linear, because you actually find the rate of each point, and then it's a whole thing, and then it's a whole different thing. So yeah, so you can only find rate for in grade 9 for linear graphs, because that's the way we like it. Okay. There are 2 questions here, but I'm actually going to leave these for now, and I'm going to put this on the next PowerPoint. So we're done. Hopefully that made sense. Again, most important parts of this lesson are making sure you understand what's linear and non-linear, which we kind of touched on yesterday. Being able to find if things are linear just by their tables. So being able to divide them like through the first differences and tell me if they're linear. And then if they are linear, can you tell me what the rate is? Which again is just dividing them, right? If it's non-linear, don't worry about it. And then the last thing is initial value. If you can understand initial value, then you are good to go. Okay. Hopefully that made sense. I'm sorry for the ridiculous technical errors we have. As I'm saying, it's just getting worse and worse, isn't it? Anyway, have a good day. I will see you tomorrow. Hopefully, I'm at the board tomorrow. Yeah, I might not have a video out for 2 days. I'll see what I can do. All right. Have a good day.